Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. In the videos about direct lighting calculations, we saw that the final color and intensity of light that's reflected by a surface is the sum of the diffuse and specular bidirectional reflectance distribution functions. So far we have been looking at light that's emitted from a single light source. However, in reality, light is scattered around in the environment, resulting in mainly indirect lighting of objects. Therefore, each object has a contribution in illuminating other objects that are sufficiently nearby. Or in other words, objects are globally illuminated. As an example, imagine we would like to calculate the lighting at this point in the scene. In addition to any direct lights, we also have to sample any light that's reflected by the surrounding and compute the contribution to the total light intensity. We could go even further and calculate multiple bounces of light in order to create an accurate image. Obviously, this is a very expensive computation, and although a number of methods exist that can approximate this global illumination problem, it is still an active area of research. One such method for approximating global illumination is by using ray tracing. However, the current hardware at this time is not powerful enough to generate good results with ray tracing alone. Additional image reconstruction techniques and denoisers are needed in order to achieve acceptable results. There exists another, simpler method, which most games have been using since the early 2000s. It's not at all as accurate as ray tracing, but since it's much easier to implement and way less resource intensive in terms of memory and computation, it's a more practical alternative to ray tracing. In this method, we render the scene at a certain camera position in all directions. So in this example, we would position the camera at this point and render the scene in left, right, up, down, front and back sides of the camera position. If we set the camera's field of view to exactly 90 degrees, we'll have the full environment as is visible from this point. We can create a texture cube from these 6 images and use it for lighting calculations. Of course, the lighting and reflections are only plausible at this particular point and will become less accurate the farther we get from it. One solution to this is to create environment maps throughout the entire scene in a 3D grid and interpolate between them when rendering each object. The texture cubes in this case are called light probes. At this time, I'm not entirely certain which global illumination technique we'll be using in Primal. However, we can already look at the math behind using environment maps for lighting the scene using only a single texture cube. This technique is known as image-based lighting, and we'll see how it's done in the next episode. Right now, however, we have another problem that we need to solve first. Since we don't have a way of rendering our scene to a texture, we can't build a cube map of our scene yet. Of course, we can add this functionality to the renderer, but a faster way to move forward for now would be to use already existing environment maps that we can download from the internet. Now the problem is that these textures often come in a format that's not a cube map, but as a single image that's called an equirectangular texture, as we can see here. This is an excellent website where we can download environment maps for free. In addition, they are all in HDR format, which means they can contain a lot more variation in light intensity. Looking closer at such an image, we can see that it wraps all the way around us and covers a full 360 degrees horizontally. In the vertical direction, it covers 180 degrees. Therefore, the aspect ratio of these images is always 2:1. You might already have guessed that we can use this image to seamlessly cover a sphere. Note that the pixels on the first and last rows of the image cover a single point in the north pole and the south pole of the sphere respectively. We can use polar coordinates to directly sample from this image in our shader. However, this involves using expensive trigonometric functions and is therefore not efficient to use. If we could convert it to a cube map, however, we could use a direction vector to sample from it, which is much faster. In this episode, we are going to prepare environment map processing for image-based lighting, and the first step is the conversion of equirectangular images to cube maps. This is relatively simple and can be done by placing a cube map inside the sphere. Then we can calculate a direction vector from the origin that goes through each pixel of each face of the cube map. We have to map this direction vector to a position on the equirectangular image. To do this, we consider the coordinate system of the direction vectors. Note that in this case I chose the z-axis to point up, and the x and y-axis are on the horizontal plane. On a sphere with a unit radius, each direction vector can be viewed as a point on the surface of the sphere. We can use basic trigonometry to find angles phi and theta that correspond to this point in polar coordinates. Now we know exactly where in the image we have to sample, and so we can convert it to a cube map. Let's have a look at the current state of the editor with regard to cube maps. Here we have the textures we had imported for our test scene. I'm going to add a folder and create a cube map here. We can already create cube maps using 6 square images with the same size. However, the editor right now isn't really great at visualizing cube maps. As you can see, although it's indicated that it's a texture cube, each face of the cube map is displayed separately as if it was a texture array. This is something we'll improve in this episode. We can also already import HDR images, such as this one. And as you can see, it's imported as a single 2D texture. Obviously, trying to import it as a cube map now fails miserably. In this video, we are going to start writing the C++ code that will convert this image to a cube map. And if you're wondering, since I already wrote all the code for this episode, I can also show you the end result. This is the new version of the editor where I can try to import the same image, but this time I'll import it as a cube map. There are some new settings here which we can use to set the size of the resulting cube map, to mirror the cube map, and to tell the importer if we want to pre-filter it. Pre-filtering environment maps is the topic of the next episode, so right now it doesn't do anything. We can import the image as usual, but this time when we open the imported asset, we see the 6 faces of the texture cube unwrapped, so we can have a much better idea of what it looks like. We can still toggle between viewing each face separately and the unwrapped cube map using this new button. I also added some animated arrows that will point to the currently selected face. And of course we still have the full MIP chain. The image can be re-imported at all times in any shape or format that's valid and supported. And here we can see clearly what the effect of mirroring is. This is needed because in general we use these texture cubes for reflections, which obviously should be mirrored. One more thing I wanted to show you before we look at the code is the fact that we can also create arrays of texture cubes. This could be useful if you'd like to use multiple environment maps. For example, some games use pre-rendered environment maps for various times of the day and interpolate between them to simulate day and night lighting. In this case, we can use a single texture resource for all those different environment maps. So now we have a 2D texture array of these 2 images, but I can re-import them as cube maps, which results in 2 texture cubes in an array. That's all I wanted to demo, so now we can go ahead and see the code. I added a new CPP file, a shader file, and a command file, which is actually just a batch file that executes some commands for compiling the shader. Converting the equirectangular images can be done on both the GPU or the CPU. Obviously, doing it on the GPU is much faster and has higher quality results because we can use bilinear sampling. However, it's easier to understand the algorithm if we look at the CPU code first, without all the clutter from the graphics API. I'll explain the GPU implementation in the next video. Let's start here with this function that takes a UV position on a cube map face and returns a normalized direction vector. The U and V parameters are normalized coordinates between 0 and 1. The result is a vector that goes from the origin to the provided coordinate on the texture. We know that each face is perpendicular to one of the x, y, and z axes. So one of the components is always 1 or minus 1 depending on the face's orientation. The other two components are u, v, or minus v. I'm sure there is an equation to determine these vectors, but I just tried different combinations till I found one that worked. This vector is then normalized and returned to the caller. The second function maps this direction vector to a coordinate on the equirectangular image. This is the implementation of the trigonometric equations that calculate the polar coordinates phi and theta on the unit sphere. We have an additional step here which maps the values of phi and theta to a normalized value between 0 and 1. Remember that phi is between minus pi and theta is between 0 and pi. The main function that does the conversion is this one here. It takes one or more equirectangular environment maps, the number of images, cube map size, whether the cube maps are going to be pre-filtered for image-based lighting, and if they should be mirrored. The result is put in the cube map's scratch image. I decided to use a constant size for cube maps that are going to be pre-filtered. This is to avoid large cube maps that don't necessarily result in better image quality. In the literature, a typical size between 64 and 256 pixels can often be found. I chose a size of 256 pixels. Since we are going to read from and write to images with arbitrary formats on the CPU, it's easier to do everything in a floating point format first. Therefore, the output format is using a 32-bit RGBA float format. In this for loop, we'll also convert each input image if it doesn't already have this floating point format. The convert function is part of the DirectX text library. Keep in mind that this function also converts from sRGB to linear RGB if the source image is sRGB. Obviously, we don't have to do these conversions manually when using the GPU implementation. Now we have scratch images for both the input and the output. We can take each environment map and sample from it for each of the 6 cube map faces. This can be done in parallel, so we spawn 5 threads and call this function for each face. The last face is sampled on the current thread. Here we wait for all threads to finish their work. Finally, if the input format differs from the 32-bit float format, we convert the result back. Otherwise, we return it as is. The final piece of code is this function that samples each cube map face. This is the core of the conversion, where we sample from the equirectangular image and write the sampled value to a pixel on the cube map's face. First, we compute the inverse of the cube map size. I should have used a single variable for this, since width and height are equal, but this is okay too. Row pitch and env row pitch are the row sizes in bytes of the cube map and environment map, respectively. We subtract 1 from the env map dimensions because we multiplied the UV value calculated by this function in order to get a pixel position. By subtracting 1, we sample the correct position when either u or v is equal to 1. We also have a constant for bytes per pixel, which is always 16. Next, we loop through all pixels of the cube map face row by row and calculate u and v such that their value is between -1 and 1. This is because we want to determine a direction vector from the center of the cube which means that half of the face pixels are in front of us and half of them are behind us. Hence the range -1 to 1 for U and V, which can be used together with the face index to get the sample direction. This direction is then converted to a UV position on the environment map, where the value of U is flipped if the cube map needs to be mirrored. Using the env map's width and height, we can convert this UV to a pixel position. Now we have pixel positions for both the cube map face and the environment map, and we can use them to calculate an offset within the buffer that contains the images. We can copy the pixel from the env map to cube map face using a simple memcopy. And that's how to convert an equirectangular image to a cube map on the CPU. As I mentioned, we'll look at the GPU implementation in the next video, but first I'd like to show you the changes we have to make in textureimporter.cpp in order to support environment map processing. Here I added 2 forward declarations for the new functions. The first one uses the GPU for the conversion, and the second one does the same using the CPU. As we saw earlier, we have some new settings which are also added to the texture import settings here. I changed this feature level to 11.1. We had a block of code here in the canUseGPU function that tried to create a device. I moved this block into a new function, and here we just return true if the format matches any of these. Another block of code that I refactored is here, which I put in a function called runOnGPU. Here we can pass a lambda expression, which contains the code that will run stuff on the GPU. I'll show you the whole file in a minute after I explain these changes. So here we have the 2 new functions I added. This one is a literal copy and paste from canUseGPU function. The new runOnGPU function expects a lambda expression. It's a template function because each lambda is a different type. Obviously, I'm not checking if template parameter t is a callable object. I didn't want to add C++ clutter for something we are only using internally in a specific way. Anyway, here we try to create a device first. If a device already exists or it created one successfully, we can run this code, which is almost exactly the same as before, except now we call the lambda function here. Previously, we set the HDR flag if the format was one of the BC6 formats. However, a texture doesn't necessarily need to be in block compression format in order for it to be used as an HDR texture. So I added this new function with this list of formats that can in principle be used for HDR rendering. Then we can call this function to set the HDR flag. Another block of code that I moved into a new function is one that generates MIP maps. It was originally in initializeFromImages function. Here we call the new function, and I also added a new condition to allow MIP generation if you want to pre-filter the cube map. The reason for this will become clear in the next episode. Going back to the topic of equirectangular images, here I added a new block that tries to run the conversion code on the GPU, and if that failed, it will run it on the CPU. Here we check if the width of the image is twice its height first. Otherwise, if we don't have a multiple of 6 images or the images are not square, we return with an error code. If that's not the case, we create a cube map using the source images. Before this point, we had a shutdown function here, followed by a decompress function. I refactored decompress into a new function, and because it's really similar to how it was, the diff tool thinks that we effectively moved down the shutdown function. So here we have the shutdown followed by decompress function, which calls decompress image function. And those are all the changes in this file. Now I'll show you the whole file page by page, so feel free to pause the video and make sure that you have a similar code. And that's everything I wanted to discuss in this video. We are going to look at doing the same conversion on the GPU using DirectX 11 in the next one. I hope there was something new for you to learn in today's video and that you enjoyed watching it. As always, thank you for joining me and I'll see you next time.